Hello, today we'll talk about famous Fizz Buzz task. Yep, I know that there are a lot of different approaches and different videos and different analysis and different examples about this task in optimizations in a very different manners by speed, by memory and so on and so forth. But I hope I can show you some interesting points from my point of view. So first of all, about some legends on this task. I don't know is it true or not, but I heard that initially this task occurs in some context, and then the context was lost, and the task now looks like is simple, trivial, and it's not too hard to implement it. But as I heard, initially there was additional conditions, additional limitations. So you have to implement this well-known task, but using as minimal amount of if instructions as possible. You know that if instructions compiles in jumps on labels in assembler code, and it's not so good for a bunch of reasons. The more straightforward code flow is, the more easier a compiler can make some optimizations, can parallel the processes, cannot have some predictors of workflow, of control flow of program execution. Yep. So anyway, having less labels, less if instructions, less conditionals in the code sometimes looks like to be better. And that way task makes sense to reduce amount of if instructions. And we will implement it this way. And moreover, I'd like to say, if you are trying to implement very simple task, and if it's so simple for you, then try to implement it in assembler first. And moreover, there are different assemblers with a different set of instructions, and some of them, for example, for the low family of AVR teeny microcontrollers, they even do not have division instructions on board. So their command set only have subtraction, addition and multiplication, but not a division and not a reminder of division, therefore. So let's keep it in mind, and then let's start to implement this task, keeping in mind the optimization in a very limited conditions. But first of all, I'd like to explain you some little tricks which are well known in assembler, like assembler related sphere, and there are a lot of text books. For example, Henry Warren Jr. Wrote an amazing book, Hacker's Delight, it calls in English, so I strongly recommend it for those of you who are interested in low-level optimizations. But let me introduce the first little moment. One time I wrote an assembler code for the task, and I found out the problem that I need to switch the entry of register between two values. For example, here there are examples. First value A is 47, second value B is 71. We set atom as value of A, means 47. And then try to create a way how to optimal way how to switch between these values 37 and 71. So please stop the video and try to think about how you can do it with conditional instructions or without it, and with labels or without it. And yeah. So, let's imagine that we can continue. And first of all, the very naive way is to use if a is 37, then set a is 71, otherwise set a is 37. But it's, as we discussed before, it's a conditional instruction. It jumps on the labels, it's not straightforward and flat code flow. So that's why there are but of different approaches and different ways. First of all, we may use this thing. We can calculate the sum of a and b and then subtract from the sum the value of variable. So let's look how it looks. 37, 71, and so on and so forth. And it works fine, and it's way better than using conditional instructions and labels. It's about one command in assembler code. This pre-calculated value we can store as a constant. Yep. But sometimes the sum of two numbers are bigger than the type upper bound, but we can use another approach. There are another way for doing it. We can calculate the bitwise XOR between a and b, and then XOR the entry of variable x with this magic number, so-called. Yep. Let's see. 71, 37, 71, 37, and so on and so forth. Yep, and that shows a little example and explains a little bit what we will do in terms of Fizz Buzz. We will do such a type of low-level optimization of excluding conditional extractions. Yep. So, but first of all, let's remember that that days the C language was common, widely used. And first of all, a little bit introduction about C strings. We will use C strings. C language has some convention that a character with code 0 is so-called terminator of string. So every print function tries to type every sequential character until it reaches 0 value. So that's why we implement our emulation of print C string function. It actually takes a pointer in the C world, yeah, a pointer, and it jumps by incrementing this pointer until it reaches nil. But here we have no pointers in closure world, and we will have a real string, and the n as a value from which symbol we can start. And yep, we can define two pre-built strings. First we'll call Fizz. It's a character 0, then characters F, I, Z, Z, and then it terminated by 0 at the end. So please keep in mind that in C it's not a nil in as a character, it's a nil as value, yeah, actually. In C code, in the memory, there will be such values: 0, the number associated with the character F, with I, with Z, with Z, and 0 again. So if we will try to print starting from this pointer, we'll print nothing, because it's already 0 from the very beginning. But if we'll start printing from this pointer, we will print Fizz, and finishing with 0 final character. And let's check. Print C string from the pre-built Fizz variable starting from the very beginning. Yep, it prints nothing. And printing it from the first character, it prints Fizz. Yes, it works the way we have to do. That was a little explanation about how C strings work and how we will use them. And then we will implement our Fizz Buzz function, keeping in mind this approach. And we will create some server's function called divisible, nominated denominator, and it's actually it's very straightforward, very clear, except only that point that it returns not the boolean value, but it returns only two values, 1 or 0. So if n is divisible by d, then we will return 1. Otherwise, we will return 0. And our Fizz Buzz implemented in mutable way with a loop old good for loop. Yep, and we calculate on each loop step the value of divisible n by 3, the value of divisible n by 5, we will call it d3 and d5. Then we will calculate some magic number. Later I'll explain what it means. But first of all, we will call print string from the pointer of d3 from the word fizz. Let's imagine that n is 1, divisible n by 3 is 0, so n is not divided by 0, so therefore d3 is 0, and print string from 0 value, like we saw here, it prints nothing. So this instruction immediately prints nothing without any conditionals. Then we do the same thing with d5 and buzz pre-built value. And then we have to decide, did we print either fizz, either buzz? And if not, then we have to print our string. We can have a bitwise OR operation between d3 and d5 and calculate, did we print either fizz or buzz? And then if yes, if it value is 1, then we have to inverse it. And inversion we use for inversion bit XOR operation, like I explained from the very beginning of this nail. And we have so-called the pointer for printing string representation. It also starts with 0 character, and if pn is 0, it's print nothing. But pn is 0 only when we print either fizz, either buzz, or both of them. So that's a little bit explanation how it function works. And we can call it and see on the terminal the right result: 1, 2, fizz, 4, buzz, 5, fizz, and blah blah blah, 15, fifth buzz, and so on and so forth. So it works fine. But only one thing we can do even better in this approach. It's a thing, how can we implement this divisible function? First of all, as I explained before, let's imagine that we have no integrated so-called operations like division, remainder of division, remainder of division, and so on and so forth. And also it has an internal explicit conditional operation if. Oops, let's pause the video and think a little bit. But we can continue. First of all, I'd like to explain you that nobody asks us to create a function which will take a random number and then calculate, do we have to print it string representation, or we have to print fizz on it, or we can print buzz, and so on and so forth. The task is about sequentially incrementing the numbers and then printing some values. So we can rely on previously calculated values. And for this sequential approach, we can find out that we will call this divisible, for example, let's thought about 3. Divisible 1 by 3 is 0, 2 by 3 0, 3 by 3 1, and 4 by 3 0, 0, 1. And that pattern 0, 0, 1, 0, 0, 1, 0, 0, 1 will repeat all the time, from 1 up to any number of 100, 200, 1,000, million, and so on and so forth. And we will implement this pattern using our conditional-less bitwise operations. Let's imagine that we have this value. It's a number 1, so only right bit is set, but all the other bits are clear. Then each cycle iteration we will shift this value left, and that will return us this value 1 shifted left, 1 shifted left, and then one time 1 shifted up to some bound. Yep, it was before this vertical line, and now it's after the vertical line. And then it means that we now find the situation, the case of 1. What can we do? First of all, we can move shift right on 3 this value. It returns 1. Otherwise, if we shift right on number 3 these previous values, it returns 0. So that's actually these zeros, and that's actually this 1. But later we can we have to actually update this value if it overfits the bound. We can create the initial value from it overfit. So organize so-called cycle buffer. How we can do it? We can use bitwise OR operation between shifted value and initial value, and we have this thing. Then we may use bitwise AND operation with mask. Mask will set only 3 first bits of the value, and AND operation with ones returns only only the ones which are under the mask, so-called. So this one will disappear, but this start one only remains. And if you'll check all this update criteria for the values which are not overfit the bound, they will do nothing with the initial values. So that's a magic operation without any conditional expressions, without any labels, without any ifs, and so on and so forth. Very straightforward code, which can be done on every numbers, but it will return the right value. So we will implement its enclosure. We will pre-build the masks. It's in a binary format. This number 3 bits set and 5 bits set, and then use in a cycle not an only number, but the masks, not masks, but some temporary values itself. First we will set them as a value of 1, then we will shift left by 1, like I show you here. Yes, then we can shift right by 3 or 5, like I show you here, to check if we have a 1 in a first bit or not, or we have 0, yep, and it's actually this 1 or 0. And then we will use the results in the same way like we did it previously, but only one trick is how we will update. We will apply mask by bitwise AND operation on OR value of shifted and unshifted values. So that's how it's implemented. It has no any conditional operations may be explicitly set, because yep, I know the string representation of the number can have internal conditional operations, and also print C string have to check if we reach 0 character or not. But these conditionals are implicit, and we cannot avoid them, because we have to use the pre-built library functions such as print string, such as convert number to string, and so on and so forth. But instead of it, all our implementation, maybe only for checking the cycle limit, yep, all the other code is very straightforward and is without any conditionals. And it works fast, because it utilizes the fast and, from my point of view, effective implementation of such type of patterns and checks. So finally, let's call it, and it returns the same result. 1, 2 Fizz, 4, 5 buzz, 6 Fizz, and blah blah blah, 15 Fizz buzz, and so on and so forth. So that's up for today's nail. Feel free to discuss in comments something interesting. Yep, and see you on the next nails.